A lot of what we know from science comes from the use of models. Models are systems that are used to stand in for real-world systems of interest called the target system. Experiments or other interventions can be carried out on a model, which can in turn give scientists some information about what to expect if that same experiment had been performed on the target system. Models are especially useful when it's impossible to do the desired experiment on the real-world target system, either because it's too large, like the sun, or it's too remote, like other planets, or it no longer exists, like dinosaurs, or if there would be ethical concerns, like testing some new drugs. Models can take many different forms, which is part of why it's hard to give a succinct definition of what they are. But they all have one thing in common. The model must be similar to the target system in the relevant respects, such that the experiment that the scientist is carrying out on the model tells them something about the target system. Here are a couple examples. A scale model is built to have the same or similar physical characteristics and proportions, but just be smaller so that it's easier to work with. Scale models are used in many applications. One is city planners building a model of a downtown block to see how different plans for a new structure would impact the pedestrian experience. Another is engineers using scale models of a new airplane design in wind tunnel tests. A fascinating example of a scale model used for scientific purposes is the San Francisco Bay model, which was used extensively to test how different projects or changes would impact the conditions in the San Francisco Bay. Today, it's very common for modeling to be done virtually, using a computer model to represent the target system. In these models, the conditions of the target system are programmed into a computer simulation, which then can be run under different conditions, simulating experiments on the target system. In fact, modeling of the San Francisco Bay is now entirely computer-based. The scale model was decommissioned from scientific use in 2000. So let's just consider these two kinds of models and ask, how are they similar to the target system? With the scale model, it's easy to see that there are some similarities. It's filled with water, just like the actual San Francisco Bay. The shoreline has been reproduced with admirable accuracy. The depth of the actual bay was not something the modelers could reproduce in scale. So what they did instead was add obstacles to the model to change the water flow, to make it so that the water flowed through the model in a way that matches its flow through the bay. They calibrated the water flow by taking thousands of measurements in the actual bay, and then use trial and error to reproduce the real behavior in the model. This allows the scientists who used this model to have confidence that the flow of the water in the model and how it changes in different scenarios accurately represents water flow in the real bay. That is to say, it's similar to the target system in the relevant respects. But how is the computer simulation similar to the bay? It's not filled with water, and it doesn't have a shoreline. What it does have, though, is a way to control the parameters of the simulation, which represent different scenarios in the bay system, and an output data set that represents the relevant variables of interest, like water level at different locations, or water salinity, or temperature. What makes a computer model similar in the relevant respects to the target system is not what it's made of, or what it looks like, as it is with a scale model. Instead, what makes it similar is that if you represent the kinds of conditions you want to test in the real-world system by parameter values in the model, you should get the same output data from the model as you would from the system. The model can be calibrated using existing data and then applied in situations where we have reason to believe that it will still be accurate. In addition to the kinds of models we've been thinking about so far, there are other kinds of models too. There are mathematical models where the target system's behavior is represented by a system of equations. There are analogical models where the notion of similarity between the target and the model is analogy. And then there are mechanistic models, where a type of phenomenon is represented graphically with an emphasis on the entities and processes that bring it about. The Bay model is a scale model, as we said, which differs from its target system in terms of scale, but also in other important ways. And then the computer simulations of the Bay are computer models. Exactly what makes a model similar to the target system varies depending on the kind of model and the application for which the model is being used. But in general, for a model to be useful, it has to accurately represent the target system in the relevant ways that allow it to stand in for that system when we want to do an experiment, but can't do it to the real thing.